All right, so yesterday we talked a lot about solvents. Solvents matter a lot for substitution reactions, and even more so when we get into the next chapter, which is why I tried to drill it. The first thing we said was that we need a polar solvent to stabilize the transition state. And we said in this handout, hey guys, let's make sure we're listening. For the top one, we've got H-bonding solvents. Next row, we've got non-H-bonding solvents, but they're still polar. And then we've got non-polar solvents. For SN1 and SN2 reactions, we want to make sure we're using polar solvents, so we don't want to use the non-polar solvents in that bottom row. And then we said for SN2 reactions, we actually prefer to use a polar aprotic solvent. That way our nucleophile is held less tightly by the solvent and is more available for attack. Versus an SN1 reaction, we said the nucleophile doesn't matter. Instead, we just want to stabilize the leaving group as much as possible. So polar protic solvents are favorable for SN1. All right. And then we said, well, nucleophile strength depends on whether or not you're in a protic or aprotic solvent. So in this case, we get more nucleophilic in protic solvents as you go down a column. However, you get more nucleophilic going up a column in aprotic solvents. And then we said nucleophiles in the same row, you get more nucleophilic as you go left. So in this case, nitrogen with a negative charge is going to be a better nucleophile than fluoride due to electronegativity. And then we said with neutral nucleophiles, when you're going up and down a column, you get more nucleophilic as you go down due to less H-bonding or dipole-dipole interactions. And then when we said if you're comparing neutral nucleophiles across a row, it gets more nucleophilic as you go left to right. So there's a lot to pay attention to. If you remember the sheet I gave you a few days ago, it's actually somewhat summarized in the bottom of the sheet talking about solvents as well. However, I like having just a nice summary table, and I've also included a link to Master Organic Chemistry. He's got another unique way of summarizing this. But I typically look at that corner of the periodic table, and then I try to develop trends. So for example, as we go right to left, things get more nucleophilic. Really, carbon's almost never a nucleophile, so we can even get rid of that. And then as we go up a column, in polar aprotic solvents, we get more nucleophilic, but as you go down a column, you get more nucleophilic for polar protic solvents and neutral solvents, so polar protic. So these trends are kind of confusing, but it's going to play a large role when we get into substitution versus elimination reactions. Yeah. This is for both SN1 and SN2. However, when we're thinking about nucleophile strength, where does nucleophile strength matter more, SN1 or SN2? SN2. So oftentimes with SN1 reactions, we just want a weak nucleophile. And in fact, we typically don't want a strong nucleophile because sometimes strong nucleophiles will do acid-base chemistry as well. So this is the overall trend that we were covering yesterday. Are there any questions with solvent choice? I know it's a lot to absorb. All right. So what we're going to do today is we're going to talk about leaving groups a bit more. And you saw some of this with your problem of the day. One good thing with leaving groups is arguably this is one of the easier aspects of substitution reactions, but let's do a quick summary. For which reaction do leaving groups matter the most, SN1 or SN2? SN1. Okay, so leaving groups are very important for SN1. Why is it really important for SN1 but not as important for SN2? It's a rate limiting step. All right, if we think about SN2 reactions, leaving groups are only moderately important. The leaving group falling off is involved in the rate limiting step, but what's the other half? The nucleophile attacking, right? So the rate limiting step also involves the nucleophile. So for SN1, it's very important. For SN2, it's moderately important. That is to say, it's not important for SN2. It's just less important for SN2. Does that make sense? All right, so let's do some leaving group comparison. All right, let's compare the following leaving groups. Which of these leaving groups is going to be better, bromine or iodine? Why? Bigger. Bigger. All right, so bigger anion once it falls off. Means it's more stable. All right, so when we're looking up and down a column, we compare atomic size. When we're going left and right across a row, we're comparing electronegativity, right? So we're going back to the cardio rules. We're assessing the stability of an anion. First thing we look at is the charge. In this case, it would be bromine with the negative charge versus iodine with the negative charge. Then we would go to atom, and we'd say, well, this atom, the iodine, is much bigger. Therefore, when it's an anion, it's going to be a lot more stable. All right, let's do another one. All right, in this reaction, first thing I would do is try to identify our potential leaving groups. Carbon's a really crummy leaving group. It doesn't like having a negative charge. Oxygen, on the other hand, yeah, it's pretty happy with the negative charge. So we'd compare this leaving group over here to this one over here. Which one do you think is more stable, the one on the left or the one on the right? One on the left, and why is that? Resonance. Anion due to resonance. All right, let's go abstract though. In the top reaction, so what I mean is, let's consider this substrate. Is that substrate more likely going to do SN1 or SN2 chemistry? So the first thing I always look at is the carbon that's going to be attacked, right? So this carbon right here, highlighted in yellow, is primary. Is that more likely going to do SN1 or SN2? SN2, absolutely. All right, this one down here, is that more likely going to do SN1 or SN2? SN1, it's a tertiary carbon. So you can also look at these and start to predict which reaction mechanism is more likely, SN1 or SN2. However, we do need to look at the leaving groups too. All right, so the big takeaway with this is the stability of your leaving group is essentially the same as the stability of conjugate bases. So a good leaving group is the same as a good / stable conjugate base. Pretty easy to remember from the cardio rules. All right, so if we look at really good leaving groups, in general, good leaving groups are the conjugate bases for really strong acids. So if we consider strong acids, like these ones over here, they're typically acids with a pKa of less than 0, right? If it's a pKa of less than 0, that's a pretty strong acid. So something like the hydronium ion, the leaving group in this case, water, would be a great leaving group. It could be lost as a neutral molecule. The next one above that is tosylic acid. That conjugate base is resonance stabilized, which is really good. And then we have the halo acids like chloride, bromide, and iodide. Why don't we have fluoride? Hydrofluoric acid is actually considered a relatively weak acid, meaning its conjugate base isn't very stable on its own. So fluoride's kind of a crummy leaving group. If we look down here, these ones in this bottom right-hand corner are considered bad leaving groups because their pKa of their corresponding acids is quite large. So in this case, hydroxide and alkoxide leaving groups are pretty crummy. Same thing with nitrogen. They're just not that stable when they fall off on their own. Does that make sense? So in general, try to think of halogens as being good leaving groups, neutral molecules as being leaving groups, and then we'll talk more about this one here in a minute. All right, so let's consider a hypothetical situation. All right, in this reaction, I've got bromide floating around, and then I've got sodium iodide in solution. Do you think this reaction will be SN1 or SN2? SN2, the carbon that we're going to attack that's attached to the leaving group is primary, very unlikely to form a carbocation. So we could go ahead and we could say, all right, iodide is going to be a nucleophile, attack in, kick off our leaving group, and this would be an SN2 reaction. All right, I'm going to leave this as a box, and then we can draw our final products over here. What is the sodium doing in this reaction again? It's just spectating, right? Do we ever show bonds to sodium? What's that? Br minus. Oh, yeah, Br minus. Do we ever show bonds to sodium? Yeah, you should never show a bond to sodium, right? I've seen a lot of students try to draw bonds to sodium or have arrows going to or from sodium. Sodium's just hanging around as a spectator. Just ignore it. It's there to bounce out all your charges. All right, so let's consider this reaction. I could also make an argument that we're on this side. Can the bromine attack in and do the reverse reaction? Yeah, absolutely. In this case, our leaving group, which was bromide, could also be a nucleophile. In this reaction, what side do you think is favored, the left-hand side or the right-hand side? Yeah, probably the left-hand side because bromide is a stronger nucleophile than iodide, right? At least in an aprotic solvent, it will be. All right, and if we look at iodide as a leaving group, that's a better leaving group than bromide. So sometimes with these SN2 reactions, you actually are under equilibrium conditions where you can favor one side over the other, and it's not necessarily a one-way arrow anymore. So in this reaction, we're not really doing a great job of forming products. We're going to favor the starting material side over that product side. However, sometimes there's some cool tricks you can do with this. This is actually called a Finkelstein reaction, where if you have a really crummy nucleophile, this nucleophile can, I'm going to ignore this side right now. This nucleophile, if it's kind of crummy, whoa, can attack in here, kick off the iodide, and you can get a new product, versus the nucleophile on this side is not strong enough to kick off the bromine potentially. Therefore, you get no reaction. So sometimes you can play tricks with this equilibrium and actually drive the equilibrium to form your products. So you're essentially using Le Chatelier's principle. As soon as you use up some of that product side, you're going to make more of the product side on the right, and then continue to use that up over and over again. So I'm not going to really push this, but you might see reactions like this once in a while where you're under equilibrium reactions. So I didn't want it to seem too unfamiliar. All right. The other thing to consider is solvent effects. It's a Finkelstein reaction. Let me see if I can spell it right. Oh my goodness. Finkelstein reaction. I think that's how it's spelled. But essentially you're playing this big game of pulling stuff out of equilibrium, even though there's only a tiny percentage of it in there. Yeah. All right, so solvent effects. Big thing to remember is that leaving groups are more stable falling off in what solvents? Polar protic or polar aprotic? polar protic. So we saw this yesterday when we were talking about solvents. So typically SN1 reactions are done in polar protic solvents to facilitate that leaving group falling off. Why don't we use polar protic solvents under all situations? Does anybody remember? Yeah, in a SN2 reaction, you have this other effect where the solvent might wrap up your nucleophile, which is undesirable for an SN2. So we typically only use polar protic solvents in SN1. However, that's not 100% the case. It's just mostly the case. Favored for SN1. Polar protic is not favored for SN2 because it wraps up / stabilizes your nucleophile. Does that make sense? I know there's a lot going on. All right, so we've got another problem. What if we're stuck in a situation where we just simply don't have a good leaving group? What should we do? So I'll show you a few tips and tricks and an example. So in this first example, let's say I've got hydroxide floating around, and I've got iodide as my nucleophile, sodium as my spectator cation. I could say, well, this iodide could attack in, do an SN2 reaction, could kick off OH, and I could substitute this on. Why do you think this reaction won't work? Hydroxide's a pretty crummy leaving group, which we talked about. That, and hydroxide's a good nucleophile, so it's just going to essentially reverse this arrow and say, no, I want you to go back to your starting material form. I don't want you to make product. Yeah?
Could you introduce like another mixture or molecule, whatever, that would react with the hydroxide and then draw it out?
That's a good point. So is there any way to make the OH a better leaving group? Absolutely. So in this reaction, it's really not favorable. Sorry, I'll come back to you. Because this is such a bad leaving group. If you were hypothetically to kick it off, it would just attack back in and reform your products, and you get none of your desired products. What was your question? Yeah, so that's the next question is there a way to convert that to a better leaving group? Maybe we protonate it. So let's make a note. We must convert OH into a better leaving group for substitution to occur. And we've got a few different options. The first one that Tia said was a really good option. Protonate it. All right, so I'll show you what I mean by this. In this reaction, instead of using sodium iodide, let's use hydroiodic acid. The fastest reaction in chemistry, bar none, is acid-base chemistry, not substitution. Yep?
In a practical sense, with this option, would it be better to add acid into the solution or pump hydrogen gas into the solution?
So hydrogen gas wouldn't be a good proton source. So you would want a good acid, and in this case, I'll show you why hydroiodic acid would be the best choice. The fastest reaction is acid-base chemistry. So this alcohol is going to get protonated super duper quick. And then our conjugate base, conveniently enough, is our nucleophile of interest, right? So if our conjugate base is our nucleophile of interest, all of a sudden we've got this good leaving group. It's water. If it falls off, it's neutral. It's nice and stable once you kick it off. So our conjugate base as our nucleophile can kick off this leaving group. We can get our substitution product, and our byproduct for this reaction is just simply water. So normally the acid you choose, you want the conjugate base to be your desired nucleophile. It just simplifies everything in this situation. Does that make sense? Pretty simple workaround. All right, so let's take a look at pros and cons of this. The pros, in my opinion, is high atom economy. Really, the only waste we made in this reaction is water. That's pretty good in terms of green chemistry. The con is a bit different. The problem with this reaction is hydroiodic acid is a super powerful acid. If you have other acid-base sensitive functional groups on there, it could do other chemistry that you might not want, right? So cons, can do other acid-base chemistry. That is unwanted. So we do have to be careful under simple situations. Yeah, it's really easy to do this reaction, works just fine. However, if you have, let's say, an acid-sensitive functional group, this is obviously not going to be a good approach. All right, I'll show you the other option that gets a bit fancier. And that is to convert your alcohol to a different functional group. And in fact, I'm going to label this as an R because it can be a wide variety of functional groups. So do you remember on your problem of the day seeing your leaving group? Your leaving group looked a lot like this unit, right? It popped off easily. So if we can convert our alcohol to something that's more stable as it falls off, it's going to be way better. Okay, so let's take a look at how we do this. Like we said, alcohols are bad leaving groups. So what we're going to do is we're going to react this with a special reagent. This is called Tosyl Chloride. And in this case, the R group for Tosyl Chloride is going to be this aromatic ring coming off. Why do you think that might be beneficial? Provides a lot of resonance stabilization, right? Conversely, if we didn't want resonance stabilization, maybe we stabilize it through dipole induction. Like we saw, a trifluoromethyl group is also a good option there. All right, so this is Tosyl Chloride. It's kind of a mouthful to write out. It's a lot to draw. What you can do as shorthand is just abbreviate it as TSCl. So TSCl is a heck of a lot easier to write. And then in the solvent, we have to be very careful here because this is a super reactive reagent. We can't use just any solvent. Typically, we use a non-nucleophilic solvent called pyridine. And pyridine is often abbreviated PYR. And the whole goal here, right, is you want a solvent that won't do substitution chemistry, but you do want it to act as a relatively weak base. We'll come back and talk about this later when we get into new types of chemistry. All right, so we've got this complicated concoction of new reagents. In our next step, that alcohol is going to react with Tosyl chloride to give us this new good leaving group. All right, so I'll show you kind of a condensed version of this. A condensed version that's a lot easier to draw than showing all of these reagents would just be to say, all right, I've got my starting material with my alcohol. I'm going to react this with Tosyl chloride and pyridine. And when it reacts, I'm going to have OTS. So this is a much easier way of showing this whole group here. This whole unit down here is the exact same thing as an OTS group, so you can abbreviate it, shorthand it, makes it a bit easier for everybody to draw. Make sense? So really the TS is this version right here. It's the tosylate group, and then it's attached to chlorine, so it's TSCl as a reagent, but once it's attached to the oxygen, it's just OTS. All right, so now we'll move on to the next step. All right, like we said, this is a good leaving group. If I have a nucleophile, let's say iodide with a sodium countercation, this iodide nucleophile can reach over, attack that carbon, do substitution chemistry, kick off that oxygen, and we can accomplish the same transformation as before. Plus, you get your sodium cation, plus, let me slide this over, you get your tosylate leaving group that has a negative charge on this oxygen. All right, so this allowed us to convert that alcohol from a crummy leaving group to a much better one. Yeah?
When we're drawing that out, we just write TS.
Yeah, so let's do the condensed version. So for our condensed version, same thing, right? Our iodide's going to attack in, kick off that leaving group. We'll have iodide down here. We'll have sodium. And then our leaving group is OTS with the negative charge on the oxygen. So if that is easier for you to draw, chemists like to use a lot of these shorthand notations just to make it easier. Yep? No, if you leave out spectator ions, I'm completely cool with that, with the caveat that sapling may not. Sapling is incredibly picky for this chapter, so reread the question a few times. Sometimes they say draw the neutral organic product. Sometimes they say include any byproducts. They're not super consistent, and I apologize about that. All right, so the question is, why might I want to do this reaction instead of using hydroiodic acid? It definitely goes the way I want it to go. That, and we're not using any acids in here, so we don't have any risk of any unwanted acid-base chemistry. So let's make some pros and cons. It avoids unwanted acid-base chem. So then the question is, well, why not do this every single time? I'd say they're all pretty stable. Let's go back up and look at the pro up here. We said the pro with using a proton source was super high atom economy. Our only waste product for the top reaction was water. If we look at this bottom reaction, we've got a huge chunk of waste coming off, right? That we now have to deal with and clean up as a chemist in order to purify and sell that compound. So the atom economy for this is much, much, much lower. So low atom economy. And it requires purification. Oop. So they're really similar tools. They're both capable of accomplishing the same transformation, but we might use one over the other depending on whether or not we want high atom economy or whether or not we're trying to avoid unwanted acid-base chemistry. All right, so let's do some practice. All right, for this one, I'm going to have an alcohol, and it's going to require multiple steps, so I'm going to include multiple arrows here. And I want to convert this to a thiol. So the question is, what would the first step likely be? So we could protonate it. That could be one option, or we could tosylate it. Let's try to do the tosylation simply because there's not a good acid where the conjugate base is SH minus, I guess, if that makes sense. So, tosylate is tosylate, like that. All right, so first step, let's convert that OH into a better leaving group. So I'll use Tosyl Chloride and pyridine. All right, when we do that, we're not affecting that wedge at all. That wedge is going to remain a wedge, right? Makes sense to me. All right, and then in the next step, we need to add in our new nucleophile, which is sulfur. So the best nucleophile is probably got to be SH minus, right? So you can use Na plus SH minus. Does anybody know what they call this reagent in an organic chemistry lab? NaSH. You're close. It is a name of sorts. All right, so NaSH is a reagent. That sulfur has a negative charge. All right, do you think this is going to be SN1 or SN2? SN2, why? So there's a few reasons I would say it's SN2. The most obvious one to me is you see how this went from a wedge to a dash? We experienced inversion, right? Inversion only occurs with SN2. What would happen if it were SN1? You get a mixture, right, of both wedges and dashes. So there's an inversion occurring, which means that SN2 has inversion. Whoop. So what sort of solvent would I prefer to run this in if I really want to favor SN2 and I don't want any competing SN1 reactions? Should I use polar protic or polar aprotic? Aprotic. Okay. And a good polar aprotic solvent, you could just grab one from the list. Really, it just is anything that doesn't hydrogen bond but has a dipole. Oftentimes you'll see DMF or DMSO or acetone as good polar aprotic solvents, and this would accomplish the transformation. All right, so let's include our reaction arrows. For SN2, we're going to do a backside intact, kick that off, and we're going to get an inversion, right? So it's a nice, simple organic transformation. All right, make sense so far? So now what I want to do is go back and complete our SN1 versus SN2 sheet. We've got all the key features we need now. And then I'll show you some common tips too. All right. So on the left-hand side, we've got SN2. really important to have a good leaving group for SN2 reactions, or just moderately important? Moderately important. And I'll say nucleophile matters too. However, for SN1, it is very important. It's involved in the rate limiting step. All right, so that's the big thing we talked about today. We said for SN2 just now that polar aprotic works best. Where for SN1, polar protic works better. Whoop. And going back, we said polar aprotic solvents work best for SN2 because we destabilize the nucleophile. That makes it more aggressive towards attacking your cation, or sorry, your electrophile. For SN1, we said polar protic works best because the rate limiting steps, that leaving group falling off, polar protic solvents will facilitate that leaving group falling off. So now we've got a good chart made up. All right, let's do some tips and tricks. Look at your carbon with your leaving group first. Okay? We've got a variety of different carbon types we could run into. We could have a carbon with resonance. Right? We could have a carbon that's tertiary. We could have one that's secondary. We could have one that's primary. And we could have one that's a methyl carbon. And if we think about SN1, which one's more likely? Left or right for SN1? Left. Okay? And then over here we would say SN2 is likely. That is the first thing I always look at when I'm making a decision about whether or not something's going to be SN1 or SN2. So for example, these ones over here, I would definitely say SN1. These ones over here, I would say these are almost always going to be SN2. The question is, what about secondary? You'd say, well, that's kind of in between. So if we're kind of in between and we're at a secondary carbon, what might we want to look at next? Well, we could go to our chart and we could find some other distinguishing characteristics for the reaction. We could look at the nucleophile next. That's what I would look at. If unsure, check your nucleophile. All right. Unstable nucleophiles favors SN2, right? Where weak nucleophiles tend not to favor SN2 because they're not aggressive enough. In general, they'll favor SN1. So you could do that. And then the next thing you could also do is check your leaving group. Great leaving group favors SN1. Moderate leaving group tends to favor SN2. However, that's way less important than your nucleophile, right? Your nucleophile tells you a lot more information. And fourth, check your solvent. And like I said, polar aprotic favors SN2 where polar product favors SN1. But students tend to get pretty confused with this chart and not know how to prioritize it very well. The big thing to do, like I said, is just simplify it. Look at this first thing. Look at the carbon with the leaving group, predict whether or not it's going to be SN1 or SN2, and then if you're tied, then go on to the other things if needed, right? The other thing to remember is when you're doing your reaction mechanism, what's one huge thing to look out for with SN1 chemistry that you don't have to worry about with SN2? Rearrangements, right? So SN1 reactions go through carbocations, they can rearrange. SN2s don't. However, SN2s, we have to worry about inversion of stereochemistry, or with SN1, we get a mixture of stereoisomers, so you might want to pay attention to that as well. And then in addition, let's go back and look at our pod super quick. If you remember, in our pod, sometimes you have these steps where you have to do proton transfers as well. So sometimes you need to do simple acid-base chemistry to get to your final product. So make sure if there is acid-base chemistry that's involved that you show all of the appropriate acid-base electron pushing arrows, just like we practiced earlier this term. All right, so that practice quiz is a little bit challenging. Like I said, try to treat it like a normal quiz. I'll post it tonight. If you have questions, email me. And then at the start of class tomorrow, before our real quiz, we'll go over any questions that you have.